systems connected to the main system like inductors, capacitors, and nonlinear loads. It may not be very easy to understand why nonlinear loads at the moment. We'll see later. It has a strong effect on system voltage. VAR creates unnecessary losses in the system because of the additional current flow. It reduces the active power delivery capacity of distributed generators. If I have a distributed generation with system with, let's say, 10 kVA capacity, and I load it up to 5 kVA with VAR, then the amount of power I can get out would be roughly only 5 kilowatts. I cannot give you 10 kilowatts of power, although it has the capacity, because the current magnitude limit has been reached halfway through because of the reactive power. So it reduces the power delivery capacity of distributed generation. This is very important to understand. The capacity cannot be utilized because you hit the current limit. You can't go further because your protective system will trip. They are set based on current limits. So what is the solution to the harmonic problem? At the converter level, we can add a passive filter. We can change the topology. We can add something called as the active power filter. Simple connection of passive filters looks like this. So this is the supply side on the left-hand side. And on this side, this is the load side. So the load is non-linear, is drawing a lot of harmonic current from the supply. It's going to distort the supply bus voltage here at the customer's connection. So what we do is we connect a L1C1, which is a tuned filter across the line inside the customer's premises. L2 is not a part of the filter. I will explain the operation of L2 later. This is the tuned filter, and we tune it to a particular harmonic, which may be the nth harmonic, which we want to remove. So at nth harmonic, we know if it's tuned, then the impedance will be 0 at the nth harmonic, and you can work out the expression of the value of L and C. Most important thing is if it is tuned at the nth harmonic, then at any harmonic frequency lower than n, this network will behave as a capacitor. I have shown at fundamental frequency it behaves as a capacitor, but actually at any particular harmonic which is lower than the nth harmonic, it will keep behaving as a capacitor. That is something I have already shown here. It behaves as an effective capacitor of a given value. So we have created a low impedance here for the filter, but through the filter. So the harmonic current now has one option to either flow through this or flow through the source. It will not be able to flow through the source right now because for the source, the reactance will be now n times larger at the nth harmonic. And for the nth harmonic, this is almost 0. We know that it's not exactly 0. It will be the value of the resistance of this network, but it will be almost 0 at this time. So most of the current will flow through the lower impedance path than try to flow through this path. So therefore, if the harmonics are flowing through this, they will not be there in the line. So the line has become cleaned out of the harmonics. So that's the way the filter operates. Why did I put the value L2 here? If I put a filter onto my premises, it's perfectly all right that I'm operating. And remember that you are making a effective capacitance at the lower harmonics, which we will deal with almost towards the end. Now what happens is I have created a low impedance path, and suppose my next door neighbor, he has some nonlinear loads where he is injecting harmonics into the system, but he does not have a filter. Now for his harmonics, there are two alternative paths. One is the first path is to go back to the supply, and the second path is to find a low impedance path through my supply in the absence of L2 through the low impedance path and flow here. If I do not put L2, obviously his harmonics will find the lowest impedance through the almost 0 impedance here, and my line will get loaded with his harmonics. My transformer will get loaded with his harmonics. My metering will read the current magnitude, not active power, get overloaded with his harmonics. So I am importing harmonics into my system. The only way I can stop is to put a reactor in series, which I can say as a detuning reactor, because now this reactor offers a reactance n times large to the nth harmonic, preventing it from finding a low impedance path. The impedance path for that external harmonic has become large because of the presence of this reactor, whereas for the internal harmonic, it still remains low. So this is very important to connect this detuning reactor. Otherwise, I land up with a problem. I am going to have much higher harmonics in my input transformer, and I don't know where it is coming from. We can also have series connected parallel tuned harmonic filters. We can connect L and C in parallel and tune it to the nth harmonic such that no harmonic current flows, because when I tune a parallel circuit, the impedance is almost infinitely large and no current can flow. But then I have to provide a low impedance path for the harmonics in the type of a capacitor, let us say, across the line. And therefore, the harmonics created by my load will flow within the capacitor here. It will not be able to flow out because of the large magnitude of the harmonic at the lower frequency, because you see at lower frequency it behaves like an inductance. So inductance means the reactance will be n times larger. The problem with this is, for one harmonic, yes, it's good, but usually we have multiple harmonics that we have to filter out. Fifth, seventh, etc., that we have to filter out. So you have to add in series different tuned filters. So one filter for the fifth, another in series for the seventh, and so on. As a result, you have different values of inductors in series, and for the fundamental current, you have a large reactive drop in series. So the voltage on the load side will start reducing because of the large reactive drop due to fundamental alone, because at fundamental it behaves like a inductor. That is one of the disadvantages of this type of a filter. So people prefer mostly the earlier one, that is the shunt connected filter, because now you can put different filters in parallel to it. One for fifth, one for seventh, and so on. You can keep adding it. So this is more popular than the other one. But highlight is this behaves as a capacitor for any frequency lower than the tune frequency. So if I have a tuned filter for the seventh, for the fifth also, remember it's a capacitor. Okay. So now we try to go ahead with the modification of the converters. This was our diode rectifier. We have seen it's not a good waveform at all. The line current waveform is highly distorted because of the diode rectifier and the capacitor operation. The line voltage gets distorted. We have to look into the current of phase control rectifiers. Here we have two problems. First of all, the current waveform is almost rectangular. Therefore, it has a lot of harmonics into the current waveform. So that is going to create harmonic problems on the system. Secondly, you will notice because of phase control, the zero crossings of the current are far away from the zero crossing of the voltage. In effect, the fundamental current is phase shifted, is made to lag the supply voltage by some angle. Therefore, if the fundamental voltage is lagging the sinusoidal voltage, there is bound to be some reactive power. So I am creating double problems. First problem was I am injecting harmonics. The second problem is I am creating lagging VAR. So this is one of the worst examples of our semiconductor circuits, and that's the reason phase control rectifiers are not the preferred option today. It is still remaining in use in the large power ratings, but less than 10 kilowatts is become totally replaced by other types of switch converters, as we'll see. Higher power, it remains because there is no, shall I say, economically viable, competitive replacement as of today. Technologically, yes, but it has to be economically viable. So it still dominates with a lot of adjustments. So the phase control rectifier is definitely a good example of something that creates both harmonic problems and VAR, and you can definitely distinguish and separate out the two. So what we want to do in the converter is that we should be able to look at the sinusoidal voltage because the supply voltage is reasonably sinusoidal most of the time, practically with less than about 3% total harmonic distortion. That's good enough. And we want to create a synthesizer current for the converters, where the current should be more or less shaped like this, with zero crossings coinciding. So the current waveform may be haphazard a little bit, but it should have the zero crossings coinciding with that of the voltage, and it should follow the envelope of the sinusoidal voltage. That is the best target, best compromise target that we can achieve. So let us take a look at some simple power circuit that was created some decades earlier. which was called as the active power factor technology, where instead of having a simple diode rectifier, we had connected a boost converter here, and the boost converter was connected through a diode onto the capacitor, and this was the DC bus instead of a simple diode rectifier with a capacitor. How did this operate? We have a shunt connected semiconductor switch in series with the inductor, and we make this switch on and off repeatedly. When I close the switch, the inductor is connected across the line so that the DC bus here, note that there is no filter on this side. The DC bus is effectively shorted through the inductor. So the expression is E is equal to L di by dt, and the current starts rising through the inductor. I monitor the current and switch it off immediately so that energy has been built up into the inductor. And when I switch it off, the energy will keep flowing out. And as per Lenz's law, in order to maintain the current flowing from left to right, the right hand side becomes positive in polarity of voltage. So the voltage across the inductor gets added to that of the supply. The voltage is sufficiently large to send energy out into the output side, the right hand side. In this system, the voltage that we monitor is the rectified voltage, which is not the sine wave exactly, but is the rectified sine wave that we are monitoring. We are monitoring the instantaneous current, and we are providing pulses to the MOSFET. Let's take a look here. For the first half cycle, if this is the sinusoidal voltage which you have used as a template for my reference control, then I monitor if the current through the inductor, which is the same as the current here, is less than my template. That means the voltage is used as a template for the current. So if I see that the current is less than the template value, I turn on the MOSFET. So current builds up. So current starts building up. I monitor the current. This dotted is my template. So current has overshot my template. So I switch off. If I switch off, the current continues to flow into the load side. So the current through the inductor starts reducing. If I see that the current has become sufficiently lower than my template, I switch on the device once again. So the current starts rising up again. So the sequence follows up, down, up, down, up, down on an average template. That is the sine wave derived from the supply for this half cycle. And for the next half cycle, as I mentioned, I get a reversed sine wave here. It will follow, and the input AC supply will become something like the bold waveform that is shown. It's not exactly a sine wave, but it's a reasonable sine wave with some switching harmonic superimposed onto it. That is a high frequency component. It's still there, I do agree, but the magnitude of harmonic has reduced, so the total harmonic distortion has reduced. But I have achieved the locking of the zero crossings of the current with the zero crossing of the voltage. This idea can be extended. Okay, the only catch here is that the DC bus voltage has to be higher than the peak of the AC supply. Because if I don't do that, these diodes will go into natural conduction, or they will be kept reverse biased by maintaining this voltage to be higher. And that is ensured by monitoring the DC bus voltage. So if the DC bus voltage starts becoming lower, then it means the capacitor energy is getting drained out. So I should be able to send in more energy from this side. So I use that information to increase the magnitude of my template of current. And on the reverse, if the DC bus voltage tends to become larger than what it should be, then I reduce the template magnitude of the current. So if this bus voltage monitors the magnitude of current and adjusts accordingly so that we have the right balance and the voltage is maintained. We can flip that topology and convert it to the bidirectional active power factor corrected converter. All that we have done is remove the inductor from the DC bus to the AC side, and we have added 4 active switches across the diode rectifiers. Now we can do the same thing here. For the positive half cycle, when the top part is positive of the source, to create a short circuit of the source, I will close switch S4. So the current flows through the reactor like this, through the diode D2 and back into the supply. So the supply is effectively shorted through the inductor. Current builds up in the inductor. I monitor and switch S4 off. If S4 is turned off, the current maintains this operation through D1, through the DC bus, through D2 and back. for the positive half cycle. The same thing can be done for the negative half cycle using the switch D2. The question then might arise, then why are we using 4 switches? Because of the word bidirectional converter. So this can be made into a bidirectional converter, because if you notice now very carefully on the DC bus, if I have a source of energy, the set of 4 switches with 4 anti-parallel diode looks like a single phase inverter circuit. So if it is an inverter, I should be able to create a pulse width modulated wave AC waveform between these 2 lines, and that can be used to feed power back into the AC line with proper synchronization. And then that inductor will serve to limit the harmonic current flow, because now you have a sine wave on the left hand side and you have a pulse width modulated waveform on the right hand side. So there is a lot of instantaneous differences between the voltages. So harmonic currents will keep flowing and they have to be limited by the reactance that is offered by this inductor. Therefore, the inductor is essential on both the parts. If you want to operate this converter as a rectifier, the inductor acts as the boost element to supply the energy boost. And if you want to operate it as an inverter, you can send power out using this inductor, which works to serve as a current filter. Such converters are the most popular converters for application with all solar systems, because this side, the energy can come from the solar panel or from the storage batteries, and you can use this to connect it with the grid. And you can also reverse the operation. That means you can use this converter to charge the battery from the grid when the solar is not there and you need them to be charged. So it works as an energy storage element also in case you have batteries here. This is the major converter that's used. You can look at the AC side voltage waveform. It's a PWM waveform, and the AC side current is a zigzag current that goes through. It has a lot of harmonics, so we are still injecting harmonic currents into the system. So the system has harmonic currents. Okay, one option might have been that I may like to put a small capacitor across the line in the case of an inverter. Then when I have an inverter, if I look from right to left, this is a PWM waveform. Then I have a L and a C filter. Then the voltage here should become nearly sinusoidal. Then the injection of harmonics into the supply should be very, very reduced. Yes, apparently it is so. But the moment I put a capacitor here, we land up with a lot of other problems. I'm keeping everything together so that we can understand the problem with capacitors right towards the end. We can't put a capacitor on so simple. It's not that easy to put a capacitor here. It's same thing whether you put a power factor correction capacitor here or you put a filter capacitor here, the operation is still the same. You can have 3-phase systems also. And this shows how you make them operate as a bidirectional converter. If this is the mains and this is your converter, if you want to operate in the rectification mode with unity power factor, the power factor is your choice. If you want unity power factor, then with respect to the voltage phasor V, the current should be aligned to it such that the reactive drop in the reactance for the fundamental should be vertically upwards. And then it tells you what should be the magnitude fundamental voltage E that you should generate here and what should be the phase difference. So you need to have a phase lock loop to change the phase sequence of this voltage E and control its voltage at E. Then only you will have it maintained at a current I that flows through. If you want to have an inversion operation as an inverter, when power will flow out from this right-hand side source to the mains, then the current I has to be phase shifted by 180 degrees with respect to the voltage phasor V, and the operation is just in inverse. Okay, this is going to be something very interesting. There are conditions when this bidirectional converter does not exchange average power on DC side. I have talked about exchange of power, rectification, inversion. They all refer to exchanges of power, but there are certain conditions where there is no average power exchange on the DC side. Number one is when the AC supply voltage is sinusoidal and current is sinusoidal of same frequency, but the current is displaced by 90 degrees. That means in my template, instead of keeping zero crossings to be coinciding as I had shown here, if the template, the dotted template was maintained at same zero crossings, then it is a near unity power factor operation. But if I shift this template such that the zero crossing of the template is at the peak of the voltage, then the current that is at the input is going to be displaced, rather lagging by 90 degree. And I can shift it to the other side and make that current lead by 90 degrees. It all depends on the template that I'm using, and that is a forced operation. Then you'll realize that there is no average power exchange, because with a 90-degree phase shift between a sine wave voltage and current, there is no power exchange. And also, when the AC supply voltage is sinusoidal and current is sinusoidal but at harmonic frequency, if my template is not a fundamental current, if it is a pure harmonic frequency current, let's say a fifth harmonic current, then also there cannot be any average power exchange, because I had shown right at the beginning there is no power consumed. Then it implies that there is no need of energy storage or energy receiver on the DC side, and a simple capacitor charged up to the requisite DC voltage will be sufficient for the operation, neglecting circuit losses. Why? Because there is no average exchange of power. So on the average, the capacitor is neither getting discharged or charged, so it should be sufficient for normal operation. In real life, yes, you will have circuit losses. The capacitor voltage will tend to get discharged, which can be compensated by a small magnitude of active power going in. Okay, so that you can compensate and keep the operation. Now we see, based on that concept, how we have an active power filter operation on the distributed generation system. So we have the supply bus here to the source impedance, and somebody has a load which is generating harmonics, so it draws a lot of distorted current, and you have a distorted voltage on the local bus. I connect another converter which is called as an active power filter, which is basically a static power converter. What it does is it monitors all the harmonic current drawn by the load and uses that harmonic current as a template for itself, but 180-degree phase shifted. So it is going to draw harmonic currents into itself, which are 180-degree phase shifted from the harmonic currents drawn by the load, which basically means that all the harmonic currents drawn by the load is supplied by this so-called active power filter, such that this line from the supply shall not carry any harmonic current. So therefore, this is going to supply only the fundamental current, and therefore this bus voltage will go back to its sinusoidal voltage waveform. This is called as an active power filter, where you will have exactly the same type of circuit I have shown, and it will be having a harmonic template inside it. The beauty of this circuit is you don't have to go harmonic by harmonic. You don't need to have one active power filter for the fifth harmonic, one for the seventh. You can have a composite template, which will be the composite distorted waveform comprising of multiple harmonics. It will generate that multiple harmonics and inject, so that all the harmonics can be neglected. What will remain behind on the line may be the switching frequency components only, because this is a switching converter, this is another switching converter. But you can compensate for most of the harmonics through this so-called active power filter. For VAR compensation on the line, we know classically we have options like fixed capacitor banks. We can have synchronous condensers. We can have static VAR compensators using thyristors, and we can have distribution static compensators, DStatComs. Most of us are aware of the use of these. Fixed capacitors are good for fixed loads. For example, I switch on an induction motor, which is going to draw lagging power factor, and I want that the power factor should be compensated. I can connect a fixed capacitor suitable for that motor and use it such that when the motor is on, that capacitor will do the power factor compensation. And when the motor is off, it gets disconnected along with the same motor through the same switch, perhaps, so that the capacitor does not remain on the line. If it remains, it might provide an overcompensation and again lead to a bad condition of power factor, because power factor can be lagging or leading. Both sides of the power factor are not good for us, because the current magnitude is higher than what it could have been. But the fixed capacitor application is not that easy in a distributed generation system, where we are having all types of converters connected into it. Again, why, we will see together. I'm just keeping all these together that we can see at the later end. Synchronous condensers are not really used in any new applications today. They are existing there, but because of its a mechanical system which needs maintenance and its high cost, it is not used in any new systems today. Today, we still have a lot of application of static VAR compensators using thyristors. You will recall that I had mentioned that any phase control rectifier generates both harmonics and as well as VAR. So therefore, they are cause of concern to us. We talk a lot about HVDC supplies, high voltage DC supplies, and each HVDC station comprises of still phase control rectifiers. So you have to appreciate that every phase control rectifier used in HVDC stations will be generating harmonics and VAR. So that at every end, you will need additional VAR compensation and harmonic compensation with every HVDC station, because we still do not have any technology established that can replace those thyristor converters at such high voltage levels. Lower voltage levels, yes, we are replacing using IGBTs, but still not implementable at such high voltage levels. Okay. But static VAR compensators using thyristors can be used because thyristors can be obtained in large voltages, they can be connected in series and so on. So what we do is we select the degree of capacitance that is required to compensate the lagging VAR of the load. And we have multiple capacitors because capacitor cannot be created statically in terms of a variable capacitance. So we have a selection of capacitances. Usually that's shall I say, the capacitors are in multiples. It's a double. I mean, if this is 1 microfarad, this will be 2 microfarads, this will be 4 microfarad, and so on, because such combinations gives me the largest combination of capacitors using the minimum number of physical capacitors. Because if I have that, if I need 1 microfarad, I switch it on. If I need 2 microfarad, I switch this on. If I need 3 microfarad, I switch both of them on. If I need 4, I switch this on. If I need 5, this plus this, and so on and so forth. So it's a sort of a easy way of creating the capacitor banks rather than any arbitrary value. The thyristors here operate as switches. They switch the capacitor into the circuit, or they switch the capacitor out of the circuit. But I cannot compensate for a need of 0.5 microfarad on the line or 1.5 microfarad on the line because I don't have such a capacitor here. To do that, we have something called as a TCR, which is a thyristor control reactor. Its objective is to create a variable reactance, okay, such that if I need, let us say, 1.5 microfarad compensation, I will switch on 2 microfarad here, and using the TCR, I will subtract that 0.5 microfarad equivalent of VAR. So I will be subtracting the VAR created by the capacitive connection by the reactive inductive compensation here, such that effective compensation comes down to the value of about 1.5 microfarad. So I make a smooth operation through this TCR or thyristor control reactor, which uses phase control thyristors. The moment we use phase control thyristors here, the line current is fundamental, will lag by 90 degrees, yes. As you shift the triggering angle more and more from 90, the magnitude of current starts reducing. So in effect, it creates a variable inductor, and the inductor value keeps increasing effectively because the current starts reducing, the fundamental current starts reducing. But this is not a sine wave. It has a lot of harmonics into it. So while we are trying to create compensation, we are definitely injecting harmonics into the line. This is a very popular technique, but it's injecting harmonics into the line. In a distributed generation, why do we need such systems? That's a big question. Well, if we have a lot of distribution system using cables particularly, and at night, most of the loads, if they are off in the night time, then you are going to get a rise of voltage at the load end because of Ferranti effect through the cables. So you have to do some sort of inductive connection at this end, where you might need the TCR to be operated alone on this end. So you have to try to keep the voltage within limit. On the other hand, the capacitor connections here will give you VAR compensation to cater to make the line power factor near unity, so that the current that's flowing from the source will be at the minimum value. So you have a need of these to be connected in the distributed generation. Of course, in terms of TCR, today we have some modern technology where the TCR can create lower harmonic currents, because one of such technology uses a unique delta connection of inductor banks along with another bank set of banks which may be Y or delta connected. The difference is, in this you have phase controlled reactors, in this you have line controlled reactors, and it can be shown with a particular ratio between the two, 60% and 40%. The harmonics created by this will be cancelled by the harmonics created by this, so that the line current is devoid of typical harmonics like fifth and seventh. They get cancelled. So you can have today some of these TCR structures where we have low harmonics. When we go ahead with D-STATCOMs operate with the same type of converters that I had shown earlier. So I have a IGBT converter here switching at PWM. The line voltage here is a PWM waveform, and it's connected to the mains through the set of reactors as usual. But here, the template that I'm using for the current is phase shifted by 90 degrees, either leading or lagging, such that this will behave either as a capacitor or as an inductor, depending on my choice. And since there is no exchange of average power, I don't need any DC power source on the DC side. A simple capacitor will do the job. So by controlling the magnitude of current, I can make this behave as a variable capacitor. But remember that you are injecting harmonic currents, because the current in this line, as I had shown earlier, is not a sine wave at all. And this can be used as a reactor or an inductor, depending on your application. And if you think the current can be filtered out by putting a capacitor, just wait for a few minutes until we see what is the effect of connecting a capacitor on this side in the presence of harmonics. So I think it is clear the current flowing out will not be a sine wave anymore, depending on what I had shown earlier for the generalized converter that I had discussed. Yes, this will be the nature of current flowing out. It's not a pure sine wave anymore. It does have harmonics. So there will be some problem coming up with those harmonics. Okay. Now we are going into the real aspect of what is the effect of connecting capacitors across the lines with harmonic sources. This will be very interesting. This is my sinusoidal source, because right throughout I've assumed that my source is sinusoidal, which is a very good assumption, because most of our generating equipments, the alternators, they do create sinusoidal voltages. This is a reactance in series. The reactance in series includes the synchronous reactance of the generator, includes the reactance of the supply system, includes the reactance of the transformers, whatever is connected everywhere. This is my point of common coupling, PCC. This is the source current, IS. I have connected some harmonic source on my side onto this point. This is a non-sinusoidal current, let's say nonlinear load, which is drawing fundamental current as well as injecting harmonic current backward. This is just a resistive load across the line. So this lot of harmonic currents that is created here will try to flow back to the source. It will distort the PCC voltage, and such that the resistance will start drawing harmonic currents also. And now I decide that I connect a capacitor across the line like this. This may be a physical capacitor for power factor correction. This may be a physical capacitor which I think is in terms of a filter for my harmonic source. This may be an indirect capacitor coming from any one of the LC filters which I had tuned at a higher frequency, and at a lower harmonic frequency, this will appear as a capacitor. It will cater to all the conditions moment I connect a capacitor. Either it is a direct capacitor physically, or it is a capacitor arising out of any filter connection. This is the network that is I'm created. So if I go into the details of this network, into the nth harmonic, you'll see that all the nth harmonic will start flowing through the capacitor right here itself, because this reactance will be n times larger for the nth harmonic. So you thought that your power factor can be taken care by connecting a capacitor, but you find that for some unknown reasons, your power factor correction capacitor is carrying a much, much larger current, because all the harmonic currents will start sinking into this. So your power factor correction capacitor, which is not perfect, it has a tan delta, it has certain losses, will start becoming hot and can lead to destruction of your power factor correction capacitor in no time. The same is true of any filter capacitor that you connect, even with a LC filter. This will have a effective capacitance and will start carrying the harmonics into it, which I referred to right at the beginning as the import of harmonics due to connection of a LC series connected filter. Things become still worse as we go ahead now. What I'm trying to show you here is the equivalent circuit of the system at the kth harmonic. I have assumed a particular kth harmonic for this structure. N is the general word, it's the nth harmonic, but at a specific value of n equal to k, this is my structure, where I still have the harmonic source here connected across the line. I've just reshuffled the structure a little bit. I have the load resistance here, which is drawing current. I have the fixed capacitor here. And on the source side, because it is the kth harmonic, the reactance is k times larger, but the fundamental source is not going to be in my circuit anymore, because it's not going to be interactive with the nth harmonic. It's not drawing any power at the nth harmonic. It's not supplying any power. So I don't need to put my fundamental supply voltage there. I will replace it by a short circuit there and go ahead with my kth harmonic equivalent circuit. At the kth harmonic equivalent circuit, this capacitor is 1 by k times, having a reactance of 1 by k times. And if you once again you readjust this into the right hand side figure, where I intentionally put the source reactance at the kth harmonic and the effective capacitance of whatever is there on the bus at the kth harmonic, there is a chance that these two can resonate. There is a chance, we don't know. It can resonate at the kth harmonic. If they do resonate at the kth harmonic, then what we will realize is, look at the phasor diagram. Vn is the nth harmonic voltage appearing across the load, because now the fundamental is not there. I'm applying superposition theorem. I am looking only at the kth harmonic system. Because of superposition theorem, I am not looking into the fundamental. So this is Vn. IRN is the harmonic current, part of that is flowing in here. Okay. But because they are having parallel resonance, the current in them can be individually very large. So you have ISN very large, and that is equal to ICN. So individually, the currents will cancel out with each other. They will not exist in the line. That is why IN will be equal to IRN. True, but individually, they will be carrying very high currents. It all depends on the degree of resonance and the damping that's provided. So as a result, your physical capacitor or any effective capacitor can carry a large magnitude of harmonic current in it in case there is a resonance with the system reactance. This can really kill your system. It can trip all the breakers. It can trip your capacitors. It can damage your capacitors because the current becomes very large. Something more important is your source current is also going to be very large for that particular harmonic. So when you look at the source current back here, when you monitor near your metering system, you'll find that your system is having a large amount of harmonic current compared to the harmonic current that you have generated. You will not be able to understand what is happening. Your harmonic current source is a small magnitude here, but the current that is coming in from the source into your premises can be very, very large, as like this, as shown here, ISN. You will not be explained that. And this current will be coming in through your distribution transformer level which is stepping down 11 kV perhaps into 400 volts, your transformer losses will go up significantly simply because you have connected a power factor capacitor at your premises. This is the crux of the problem. You just can't do that. You cannot connect an arbitrary power factor correction capacitor in your premises. You cannot connect an arbitrary filter in your premises without checking for resonance with the system. How do you know what is the source reactance? That's a very difficult question to answer. You need to get some idea about the short circuit ratio of the source at your premises. And that is the only thing that will give you a hint of the source reactance that's going to be present. Okay, that means with a hypothetical condition that you create a short circuit, what is the magnitude of current that will flow? Because under short circuit, and hypothetically, the magnitude of current that will flow is going to be limited only by the effective source reactance. So unless you know, get an estimate of that value, you really can't predict. Otherwise, you could have modeled it and taken a decision whether you will connect the capacitor or not. As an example, if you try to connect the capacitor at the output of that inverter that we talked about right at the beginning, let's go back there and see. Yeah, okay. So this was drawing non-sinusoidal currents as an inverter. This was perhaps solar sending out power. So I thought I will connect the capacitor here. So an inverter with a LC filter will create sine wave voltage. So this should be good to connect to the system because the sine wave voltage will not send out harmonics. Yes, you are right. But we are overlooking that the connection of the capacitor here is being made directly onto the main system, and you'll land up with the same problem that I showed there. So what is the remedy? You do connect a capacitor here, but after the capacitor, put another reactor to detune. So you will land up with not using a LC filter, but you will land up with using a LCL type of filter. That is the reason why we use a LCL filter, because you have to detune your system, prevent taking any risk of going into a resonance with the system. So if you have an inductor, let's go back to that network. Yes, if you have an inductor, additional inductor put in here on the source side, the total inductance here will be detuned from the specific capacitor, because remember, this LS, I had assumed that the value of LS was getting tuned in parallel to the given value of C. If you change the value of any one, sorry, either LS or C, you will be able to detune them. So if you add an inductor here, it is no more going to remain in resonance. If I connect a filter here tuned at the 7th harmonic, there is a chance that at 5th harmonic, this might resonate, because the 7th harmonic filter will behave as a capacitor at 5th harmonic, and it can resonate with the source. So this is a risk that we always run with the system because of the presence of harmonics, and the harmonics are created by us only because of the use of power converters. So we have to be very, very careful on a distributed generation system where we are going to have a lot of harmonics that is going to be injected into the line from different frequencies of harmonics, because we have different switching frequencies, different topologies of converters. We have to be very cautious in application of any types of capacitors or filters onto the line. Otherwise, we land up with more problems created by us than that was there. With this, I come to an end of my presentation. If you have any questions, I will answer them. Thank you for your patient hearing.
Hello.
Yes, please.
Hello. Am I audible?
Yes,
Hello.
please.
Thank you, sir, for such a cognitive session. It's always been a happiness to attend your any technical sessions or talk. Once again, on behalf of Electrical Engineering Department of Narula Institute of Technology, I want to thank you from core of my heart. Now, sir, I am going to read out some queries which has asked by the participants.
Please.
The first one is, in case of bidirectional power converter, if
Yes.
complementary switches are operated.
Mm-hmm.
In case of bidirectional power converter, complementary switches are operated. Is it possible to operate complementary switches?
Okay, I did not understand the full meaning of that question, but I'll go back. and try to answer. Okay. Is my slide visible?
Yes, sir.
Okay. Just 1 minute. So complementary switches means S1 and S4, S3 and S2. So the rule is that anytime if I operate any one of these two complementary switches, there'll be a short circuit on the DC bus. So only one will operate at a time. But you cannot leave a gap in between. If you leave a gap, your waveform, nature of the waveform will change. So either S1 will be on or S4 will be on. It will operate always like that. So that's what I understood from the question. But in case it's not very, I mean, that's not what that's not what was meant. The question can be reframed once again and asked.
Okay, sir. Sir, the next question is why LCL filter have to use instead of LC filter? Can you please
Oh
elaborate
yes,
in
yes,
1
yes,
second?
yes. Uh, See, if this is a solar system, then this is working as an inverter straight away. This figure gives you the straight away operation of an inverter. You have a DC supply, you have an inverter, you create a PWM waveform here, and then you have an inductor in series. This whole system actually is equivalent to a synchronous machine, synchronous generator, because you have a fundamental here, and you have this can be thought of as the synchronous reactance of a synchronous machine. So at this end, you have a fundamental voltage created through the inverter with a series reactance, and then you should be able to synchronize it to the grid the same way as we synchronize a alternator onto the grid. So it's a synthetic alternator. It's not a real physical rotating alternator. You use the same logic to connect it. Now, when we have a L, this is a L, which is a current filter. At the same time, it's it's used to interface. If you connect a capacitor here on the right-hand side, then when you're connecting to the grid, this capacitor on the right-hand side is getting connected straight onto the grid. Now, any capacitor connected onto the grid creates two problems. Number one problem is that capacitor will start drawing the harmonic currents created by any harmonic source on the line. Plus, in case there is a resonance with the grid reactance, then that capacitor will start drawing very large magnitude of currents, much more than what the harmonic source is creating. So therefore, you cannot connect any capacitor directly onto the line, even though if it is for a LC filter. So you have a capacitor here and then put one more inductor on the other side. The objective of putting this inductor is to prevent this capacitor from getting connected in resonate mode with the source reactance. So it's a sort of decoupling from the source. The right-hand side is now the AC source. So it's decoupled from the source.
Thank you, sir, for such a elaborative explanation. Sir, next queries is when we are using active power filter for harmonic compensation at PCC, then
Yes.
it acts as an inverter. Then what
Yes.
will be the direction of compensating current fed by the filter at PCC?
Okay. In this slide, if at any instant, if the particular fifth harmonic current is flowing from left to right, how do we decide? Because in AC, there is no real direction of current. It is decided by the positive half cycle and the negative half cycle. So, okay. So if we put a phasor saying that the phasor is from left-hand side to right-hand side, as we shown here, then at the same instant, the harmonic current generated by the active power filter for that particular harmonic should be as shown here, such that at this point, they will sum up to 0 and there will not exist any component on the left-hand side. So I put one phasor of here, another phasor here. If I go in terms of half cycles, then if the current into the load has a positive half cycle here for that harmonic, then the current away from the power filter will have a positive half cycle at that instant, such that there will be no instant either positive or negative half cycle at that instant on this line. So you use the template accordingly. That's why I said the template is shifted by 180 degrees. So if the current drawn is used as a template, you shift it by 180 degree, you flip it basically, and use it as a template for the current drawn by the active filter. Then the current sent out is in 180 degree in opposite. It comes in the other way. The objective is that it should be nullified for the source current.
Okay, thank you, sir. The last question is, what is the difference between ordinary buck boost converter and SEPIC converter?
Okay. I don't want to go into this for a different reason, because I understand this topic will be dealt with by another speaker, Professor Shiv Shankar Saha. I spoke with him yesterday, and so he said he's going to talk about DC to DC converters. So I think I'll leave that for him.
Okay,
I had the benefit of knowing that he's going to speak about it. That's why I could say that.
Okay, thank you, sir. Now I request our respected head of the department to end the session with the conclusory speech. Thank you, sir. Thank you, madam.
Thank you. Thank you.
Thank you, sir, for such a nice and elaborative lecture, and what could have been the best possible and simplest manner in which you have explained the details of harmonics and compensators. So from our end, as a token of appreciation, I'd like to share a screen, sir.
Yes, please. Thank you.
Of your certificate of appreciation, which will send you via mail also.
Yes.
Is it visible, sir?
Yes, it's coming up. It's visible. It's coming up. Thank you very much.
Welcome, sir.
Thank you.
Welcome, sir, and thank you, sir, for being with us, for sharing your precious time with us as well as your knowledge. So we look forward for more such sessions in our future program. So good day and stay safe and healthy. Sir.
Thank you very much. And thanks to all the participants.
Okay, sir. So
Bye.
once again, goodbye to all the participants. Thank you to all the departmental faculty and staff members for cooperation. We'll meet again in the second half for the hands-on demonstration session at sharp 1:55 p.m., where Professor Bishendu Chatterjee would be delivering once again his demonstration.
Okay.
Okay,
bye.
sir. Okay, sir. Goodbye. Good afternoon, Vishentuda. Welcome.
Good afternoon.
ঠিক আছে, একটু wait করো. Just wait. Let me see if the streaming has started.
কথা শোনা যাচ্ছে তো?
হ্যাঁ, একদম clear. দেখে কি বলে সবাই. Okay, so it's time. Good afternoon to all the participants, faculty and staff members of the department. So our distinguished speaker, Professor Bishendu Chatterjee, is once again with us for the hands-on demonstration for the second time. So I had already introduced him earlier, so I will not repeat. So I would request once again Bishenduda to start the session.
Thank you. Straight away, I am starting the lab session so that I will be presenting now. Uh, Please see whether the slide is visible or not.
Yes, it's visible.
Yes, it's visible. So we are starting our day. It is my second day. So earlier I have explained about the preliminary things that are registers and how to set the bit or clear the bit of a particular register, and ultimately we have linked a LED in the program, and also we have set the delay period using the timer register. This was done yesterday. Now today we will look into application, and this application is a servo control. Now this servo control has innumerable number of applications, right from the printers, scanners, plotters, everywhere. Now, what is servo? Servo is a rotary actuator that allows for precise control of angular position. Whatever I feed the angular information into it, it will just go into that position. What is the limit? It is from 0 degree to 180 degree. Now, how does it work? It consists of a suitable motor coupled to a potentiometer sensor for position feedback. This is the classical position feedback control that we study in our control system. Now, if you see, how does it look like? This is a very small, this is hardly 1 inch. So this is a very small structure, and you can easily buy it online. In some Arduino kits, the servo is incorporated, or servo is supplied as accessory to study how it works. This is for our learners. In learner kit, it is included. Look at the 3 pins. This is, first of all, this is the actuator arm where you can connect different type of controlling units. This is the output shaft, and for the input, it can be mounted by 2 screws provided here. The slots are provided here in any position where you require. And for electrical connection, there are 3 pins. The brown color pin is the ground. Almost all the servo follow this convention. The middle one, the red one, is the positive, and the orange one, on the right side, as you can see, it is the control terminal of the servo, where you can, with this help of this terminal, you send the control signal to servo so that the servo can turn at a desired angle, and that is desired by you. This is the PWM control. If you see what is inside it, the motor and a gearbox arrangement is there so that the servo can produce high torque. This motor is high speed low torque, whereas due to gear reduction it becomes low speed high torque. Speed of the servo is not the matter. The main thing is the angle that it is rotated according to our will. The potentiometer is attached directly to this shaft, and this potentiometer and the motor is controlled by a control circuit. Now if you go to a basic circuit diagram, this potentiometer is controlled by the main shaft of the servo. Main shaft, directly this potentiometer is connected. If you see, this is controlled by the main shaft, and there is a set value. Suppose this set value is 4 volts. Now the potentiometer one end is connected to ground, simplest. Another end is connected to 5 volt. The motor will turn and move the wiper of the potentiometer. I repeat again, if you see if the gear rotates, the shaft of the potentiometer is coupled to it, and the wiper inside the potentiometer turns along with the shaft. So the value is changed. The motor will rotate in such a direction that the comparator gets the same 4 voltage. This is 5 volt, this is ground. So somewhere near this point it will achieve the 4 voltage, and when these two values are equal, the motor will stop rotation. That means at that angle, particular angle, the system will stop. According to the set value, now if I suppose that is 90 degree for 4 volt. Now if I make it 3 volts, obviously the potentiometer will turn more towards the ground. So from 90 degree, it will be less, some value less than 90 degree. So it will turn in the other direction. In this way, the set value controls the position of the servo. Now, how this set value is controlled? Directly, we cannot put a voltage here. The control circuit has some internal ICs inbuilt, and that IC takes the value, not the voltage, but the PWM input. The pulse width of the PWM input controls the angle the servo will rotate. This is the basic thing that will make our system work. Now, how to control the PWM? As I have told you, the input requires this pulse width modulation, and what is the 0 to 180 degree rotation? What is the things that are required in PWM? First, the time period. It is required standard of 20 millisecond. That we know, the standard 50 hertz. 20 millisecond is the time period required, and the pulse width starts from 0.6 to 5 millisecond, which servo turns at 0 degree, and 2.5 millisecond it turns at 180 degree. So between these values, from 0.625 to 2.5 millisecond, any value will turn accordingly the servo, and we will give the desired angle we need. This is 0 degree and this is 180 degree. For example, if I want to turn it at an angle of 90 degree, I put the pulse width in the mid position, this much. So we will control this pulse width and set the angle of the servo. This is how it is controlled. Now, how to set this time period and control the pulse width is our main objective of today's lab. Once we can set these things, if we connect the servo will operate automatically. Now let us see. How to enable this PWM in Atmega, that is the Arduino board. Yesterday we have learned timer 1. We already know how to set the time period in timer 1. But this time only timer 1 is not sufficient to control the PWM. Some other registers are required to set the pulse width. Now how it is done? Let us see. First of all, a recap of timer 1 control registers. We have already stated that this timer 1 is a 16-bit register and the control register is also 16-bit. Yesterday we have encountered only the second half of the register, that is TCC-R1B. This is the timer control register B part. Now what happens here? Only this register won't do. We will have to take the total unit as the register with TCC-R1A and TCC-R1B. Now what will happen? First of all, let us start with our known thing, that is the prescaler or the clock setting of the timer. If you remember, this CS 12, 11 and 10, these 3 bits are going to control the prescaler. Yesterday we used 101 here, but today we need a faster time interval. We will need some other values. Today we can use 010 for clock divided by 8. Yesterday it was clock by 1024. So we have set these values 010. Now in your notepad you can note the 2 placeholder of these registers of 8-bit and 8-bit, and it will be required later. First of all, these bits are unknown dashed bits, so just put them 0. These bits are not required by us, so put these bits 0 in the preliminary stage and put these bits blank. The other bits that I have shown in this slide, put it blank. And what you do, first you fill the known values with the increment of clock. This is clock by 8. The timer 1 will approach per 8 clock pulses. This is the basic thing. So we are going to fill it with 0, 1, 0. So this part is filled. Next part, how to enable PWM in Atmega. I tell you, if you put any value other than 0 value, the timer 1 will immediately start operation. You see, by default it was 000, the timer was stopped. Now you have, as soon as you have put it is to 010, the timer starts its operation. But The PWM did not start, only the timer has started. Now, how to start the PWM? You will have to now use another bit. This is the WGM 10 to 13. That means these 10 to 13 bits will start operation of PWM. These are 4 bits. Obviously, there must be several combination. There must be several modes. This is table 15.5 in datasheet. Consists of several modes for which we will be using only the mode number 14. This mode number 14 is the first PWM mode. At this stage, we will know only this thing, that if you put 1110, it will be only in the first PWM mode. What is that? First PWM means it will undergo no correction. Straight away, it will operate as PWM. There are other modes like corrections, phase corrected, frequency corrected, etc. It will not do any correction. It will just run as it is. So how to give these bits? Remember, these 2 bits, these 4 bits are not in the same part of the resistor. If you see, it is distributed into 1, 2, 3, 4. These 4 bits. Now, look carefully. This is 1, 1, 1, 0. 10 and 11 is 1, 0. 10 is 0. 11 is 1. 12 and 13 are both 1. So 12 and 13 are both 1. 10 is 0. 11 is 1. So in your notepad, you can put these values. As soon as you fill this, what you will find, this register is completed. See this binary code? So immediately the code is set that we will give TCC R1B equal to this amount, this value. So this part of the register has been completed. Now what is remaining? This part is remaining. TCC R1A. We will be coming next. Now we have set the look at the mode 14 that we are going to set. Another 2 register has been mentioned that these register will be required to control the PWM time period and pulse width in the data sheet. We will meet these registers again later. But at this stage, what we are more important, we will emphasize more, is the control of the fast PWM. Even for this fast PWM, there are several sub modes. We will consider one of the mode, and that mode, the sub modes are considered by the bits of TCC R1A. That goes from COM1A1 to COM1B0. These bits were remaining in our TCC R1A rest field. Now these bits will control the sub mode of the fast PWM. Let us see a table in the datasheet, table 15.3. If you search in the datasheet, you will easily find that this is the table 15.3. There will be the fast PWM mode, and the sub mode is this. This we are using clear OC1A, compare match, etc., etc. What we don't understand at this moment, but we will use it as COM1A1 and COM1B1 as 1, COM1A0 and COM1B0 as 0. First of all, let us fill with this value, and we will understand these things later. So 1A1 and 1B1 is 1, 1A0 and 1B0 is 0. So 1, 0, 1, 0 will be filled by this in this TCC R1A bit. And ultimately, the things in the datasheet means that as soon as you set the sub mode, first PWM mode is the main mode and this is the sub mode, what will happen? The time period of timer 1 will be controlled by a register named ICR1 and the output pulse duration will be controlled by another register named OCR1A. So these two registers are now introduced. One will control the output pulse duration, another will control the time period. So as soon as you complete these bits, so these two registers are complete. TCCR1A will be this value and TCCR1B will be this value. So what will happen? We will put these two codes in our main code. Now let us understand about the time period, pulse width and the register controls. See, I have told you earlier that the Atmega chip has only 28 pins. Now only 28 pin cannot cater the several needs the IC has in its 300-page datasheet. So each pin performs several other functions other than port pins. What happens? One of the pin can function as PWM output. Not only one pin, there are several pins. A pin called OC1A pin, which is physical pin of a microcontroller, we will see which pin is that, can control the PWM status. And what happens? Timer starts at 0, that we have already known from yesterday's lab. Timer 1 starts at 0 and timer 1 resets to 0. This duration is the time period of timer 1. As soon as timer starts at 0, this pin becomes high. OC1A pin. It has become high. It will continue and the timer also continues. Now OCR1A is a register in which you can put different type of values. Suppose I have put XYZ. Now as soon as the timer increments, as soon as the timer matches the value given in OCR1A, the output becomes low. I repeat, timer starts at 0, output becomes high, this OC1A pin. As soon as the time period, the time or the increment of timer 1 matches that of OCR1A, this output goes low. The timer again continues to increment. Now the timer, instead of overflowing, because we have set the two modes, time period and pulse width, now instead of overflowing, as soon as it meets the ICR1 register value, it increments an ICR1 register. We can give another value to this register. The timer 1 resets and starts from 0. So this period will continue. If you change OCR1A, dynamically the pulse width will change. It is very interesting. Right from the next instruction cycle, this value will change. You can dynamically change this value and see. We will see that. So ICR1 will control the time period now of the timer, and OCR1A will control the pulse width of the PWM. This is the gist of PWM control in our Arduino board. How this will happen? Just I recapitulate from our standard timer operation. If you remember, Yesterday 1024 clock cycles, the timer register increments by 1, completes 65535 increments, overflows, overflow flag is set. We have seen that flag by TOV1, and to increment it took a time. We have waited until it overflowed and the flag was set, and that period determined our time delay. In this way, yesterday we have seen the timer to work, and as soon as it overflows, it sets the flag and the timer resets to 0 and starts from 1. Now today what will happen? Timer register starts from 0. Here one thing I repeat, yesterday it was for 1024 clock cycles. Now it will be only 8 clock cycles. Today this will change because I have changed the clock setting or the prescaler. So per 8 cycle timer will increment by 1. It will be faster. Now let us see per 8 cycle timer increments and OC1A pin from timer register initially goes to high. So this is the high period started. Now it increments by 1. We have given a value to another register OCR1A. Remember, these are all 16-bit. So the total time period, pulse width, everything is controlled by 16-bit, which is a very precision control. So timer register matches OCR1A and OC1A pin goes slow. This is the high period. Timer register continues incrementing. Timer register matches ICR1. Now it resets and starts from 0. What happens? This is the low period. This is the total time period. This is the high period of the time. This is the low period of the time. So in this way, high and low continues and the PWM cycle slowly proceeds at the time period set by us. Now we will have to set it according to our requirement. Note that register ICR1 and OCR1A. These registers are required to be filled by our respective values. How to adjust PWM time period? First of all, two things, time period and pulse width. So we will start with time period. Now timer 1 is a 16-bit register with 16 megahertz clock and prescaler divide ratio set to 1/8. To count from 0 to 65535, this is the full of the timer 1. The time period will be 33 milliseconds. Since this is more than 20 milliseconds, ICR1 will have to be adjusted. Otherwise, I have waited. I have given the ICR1 full value of 65535. But it will not happen. It is 33 milliseconds. It is more than 20 milliseconds. So we will have to wait and put the ICR1 some value so that it is the time period is cut short from the full value. Let us see. This is the standard. The span is 32 milliseconds. If it to complete the whole 65535 increment, but we will need 20 milliseconds less than this 32 milliseconds. So we will not allow to give all the full value of the timer increment, the value of 65535. So what we will do now, we will put ICR1 the value we require. Let ICR1 equal to X. A preliminary equation gives you ICR1 is equal to 40,000. Because this is 6, this is minus 3, it will be 1000, and x is 20 into 16 by 8, that means 40. Very easy. ICR1 equal to 40,000. Remember, deliberately we are putting the code in decimal. If you remember yesterday's class, if I put 0x preceding this value, it will be in hex. I put 0b, it will be in binary. Now I have put nothing, only 40,000, it is decimal 40,000. So that makes our computation easier. This is the advantage of Arduino, that everybody uses it right from the beginner, that any value, if you cannot compute the hex value, if you have jumbled up with the hex value and binary value, etc., directly if you put binary and put the register values, you can give it. If you have x values in datasheet, you can put that directly. Now I have decimal value, I can also put that directly without any problem. So I have given ICR1 equal to 40,000. Now what will happen? Now see, the green part was the total part, and now it is cut short to only the blue parts. It was 32 millisecond. Now as soon as timer register matches ICR1, the time period is cut short to 20 millisecond, because we have given deliberately 40,000 to have this time span of 20 millisecond. Now what happens? We will get the time period just by putting this value and nothing else. So if you put it, forget about time period, it will automatically control, and you will get 20 millisecond time period. This part is over. So let us move on to the next part. How to control the pulse width? Remember that OCR1A resistor. Now IC1, this resistor ICR1, we have already set to 40,000. So OCR1A, we can adjust between 0 to 40,000. If you give 0, the output will be totally 0. Totally, the output will be low and no pulse will be given. If you give 40,000, it will be set high for the total time period. So there will be no question of high or low. So you will have to set some intermediate values between 0 and 40,000. Code is very simple. OCR1A equal to any value between 0 and 40,000. You can give 2,000, 2, 500, whatever you like. Then the pulse width is automatically set. So we have now set the pulse width, and already we have set the time period. Now come to the hardware part. If you see, recapitulate this IC pin, I have told you these pins perform several other functions. For example, PC3 can also perform as ADC3. In this way, if you look at this PB1, port B1, it can perform as OC1A also. Now look, this pulse width modulation or the pulse width is an output. We need to drive this signal out from the microcontroller. And who decides this output and input? It is the DDR register. So at first, we will configure the DDR register so that this port B1 or PB1 is at the output. Then by filling the value of the timer control registers and the PWM control registers, automatically it will be operated as OC1A. So the output will be PWM. Okay. Now let us go to a LED glow code. Remember that yesterday we have set the timer, delay, and the LED glow was between 0 and full glow. The LED glowed full and 0 in a timely manner. But now what we will do, we will adjust the glow of the LED with the help of this PWM. Let us understand this code. The two parts you remember, one was the setup in this brace. It was the setup to run only once, and this is the loop which will continue. Let us see. First, bit set DDRB PB1. Why? I need PB1 to be output pin. Otherwise, PWM output will not be seen. So, set PBR1 or OC1A pin as output. Now, if you have noted in your notepad, TCC R1A will be this value and R1B will be this value. These values already I have explained in detail that we have filled this register. The last 3 bit was the clock control of 1/8, and this 1110 was the main mode of first PWM, and 1010 was the mode of the sub mode of first PWM, where ICR1 and OCR1A control the time period and pulse width respectively. So initially we will put ICR1 equal to 40,000. Why? If you remember, the time period is needed to be 20 milliseconds. We will not change this value, so it will run once only. What we will change? The OCR1A. Now see the dynamic system of this, or the advantage of this microcontroller. As soon as you give OCR1 equal to 4000, the pulse width set by this register is 1/100 low. Because see, 40,000 is the maximum value. Now I have set the output to 1/100. I am giving a delay, internal delay routine, not our routine yesterday that we have learned, because we are actually omitting the code and making it simple, because this is not the main thing to learn. This delay is not the delay of pulse width. This is the delay we need how long we want to see the glow and nothing else. If it is 2000, the glow will stay for 2 seconds. But the glow is controlled by this, all these resistors. Now OCR1A pulse 1/100 glow stays for 1 second. Now I have changed dynamically to 1/4 of the glow by giving it 10,000. The glow will change, and we are delaying again 1000, and I am now lastly giving total of the 40,000 for full glow. What will happen? 1/100 glow for 1 second, 1/4 glow for 1 second, and full glow for 1 second. And since this is in loop, it will repeat. So this is about the software. Just copy this code and paste into the IDE of the Arduino. It will look like this. This button is the compiling and this is the uploading. So we will compile and see whether there is any problem or error out there. It will tell you to correct this error. For example, the semicolon is missing, etc., etc. Now, before uploading, we need to connect the hardware. For that, recapitulate the circuit diagram. Look it very carefully. Where is our PB1? Here is our OC1 or PB1 pin. Where it is connected in Arduino board, this is ~9. This sign means this pin is PWM enabled. And this is the pin number 9 marked in the board. I repeat, PB1 is connected to pin number 9 of Arduino board. And this can also act as PWM control. This sign tells you in the board. They have their own sign. This is not the microcontroller sign. This is the board sign. So, along with this pin number 9, 10, 11, if you set, these pins also can give you PWM output if I change in the resistor. At present, we are only working with pin number 9. Now see, this is this pin number 9, the same pin. I have connected the positive terminal of the LED through this resistance, 1 kilo ohm resistance. The ground pin is connected to the negative pin of the LED. Simple circuit. This is the hardware circuit. Next, we will connect this USB socket to the USB of the computer. And then we will just run this upload button so that the code is uploaded into this board. Let us see what happens. I'd request you to tell me whether the video is working or not.
সাড়ে এগারোটা পূর্ণে অ্যাভেলেবল নর্মালি আসেন 10টা তারপর রাউন্ডে যান সাথে দেখা করেন রুগী দেখেন কাজটা কি করতে হবে।
Is this video visible?
Yes. Yes.
Oh, thank you. Then I explain. Now let us see, it is the minimum glow. This one is the 100 glow, and the intermediate this one, and ultimately this is the full glow. It toggles between 1/100, 1/4 and full glow alternately in the loop program, and each glow stays for 1 second because the delay we have given as 1 second. This is the demonstration. Now we could control the pulse width and the time period successfully. Now let us concentrate in our main thing, that is the servo control. Now how to control the servo? Time period required 20 milliseconds, that we have already set. Now to set the pulse width, and the pulse width required for 180 degree is 2.5 millisecond, and for 0 degree it is 0.625 millisecond. Okay. So how to do this? OCR1A register will control this pulse width, obviously. Now 40,000 is equivalent to 20 millisecond. What we need? 0.625. Okay. Sorry, there is a typing mistake. It will be 12504.625 millisecond. This is a mistake. Sorry, it will be 0.625 for 1250. Now we need a pulse width of 2.5 millisecond for 180 degree. We know 40,000 is equivalent to 20 millisecond. So 2.5 millisecond is equivalent to 5,000. So maximum value is 5,000. So OCR1A resistor will be controlled between 1250 and 5,000. This is the 0 degree, 1250, and 5,000 is the 180 degree. So this part is already we have understood, nothing to understand more. But in the loop, what we will do, it is changed. First, we will 1250 pulse width minimum set by this resistor. Now I have deliberately given a more time because of the problem in the video transmission. Because we need to see the movement, I have made it deliberately slow so that 1250 will be your minimum, that is the 0 degree, and 5,000 will be the maximum 180 degree, and it will again loop 0 degree and 180 degree. You can see. So what we will do, we will paste our code here, compile it with this button, and before uploading again we need to set this servo hardware. Remember that this brown pin was ground, red pin was at 5 volt, and this orange pin was at PWM control. This we will connect to the board, red connected to red, black connected to brown, and the orange is connected to this pin number 9. This 9 is the PWM control. Now you can just upload the code with this button with the help of USB connected to the Arduino board. As soon as you do that, you will see this demo. It is 0 degree. It is turning. If you face any problem, please tell me. Now again it will go to 0 degree. Again it is in loop, so it will operate. Now what is important is this, not the control, but if you see, it is exactly not 180 degree, and that is the problem. See, if you follow this line of the clamp, the straight line, it is going, and it is the ultimate position is something and the angle with this clamp, so it is exactly not 180 degree. Some problem is there. It is not 180 degree. That you just observe it carefully. Now what will happen? This is caused actually by low cost servo error. You will have to compensate it by observing a few cases. Practical error will be there. So if you use this low cost servo, precision servo with very high cost have several internal circuit to compensate for this. But for this low cost system, you will have to compensate for the servo. And that is another important part. By trial, let us run the code with, instead of 5,000, I have run with 5100, and the minimum value is 1075. Now let us see what happens. Just put this code, change these two only values, and compile and upload to this Arduino board. Let us see the demo. Now if you observe, see the angle, it is almost 180 degree. It's very difficult to see with the help of this video. That is why practical demonstration is required. See, it is almost 180 degree. If you observe the whole lines, it will be parallel to this clamp, almost parallel to this clamp. Yes, see, almost parallel to this clamp. So calculation of error, if you see near 0 degree range, the actual value was 1250 as written in the data sheet. But we have put 1075. That is 14% less value will be required to compensate for it. Near 180 degree range, I have given 5100, so that 2% more value will be required to compensate in the range of 180 degree. So what about 90 degree? With the help of 5100 and 1075, we can run for the 90 degree with 3088. So 3088, if you put OCR1A equal to 3088, we can run at 90 degree. So just initially it is on 1075 is at 0. Instead of 180 degree, I have put 3088 for 90 degree rotation. I have put here 3088, and now if you run, what will happen? Let us see. Again, it is now rotating, but this time it will rotate near 90 degree. Now again a problem with the video. It is not exactly 90 degree if you see in front of you. It is something different than 90 degree. Okay, it seems 90 degree, but it is exactly not 90 degree. Now we will have to compensate for that. Let us see. Let us try by trial. Let us run with OCR1A equal to 3100. So I have changed only this value to 3100. Paste the code and again uploaded 3100. In video it will look like same, but it is now exactly 90 degree. Okay. Now what is the error? Observation for 90 degree. The actual value required was 3125. Now I am operating at 3100. If you compute that 0.8%, this is very low. Almost at 90 degree, the servo is operating satisfactorily. Now from this observation, you can draw some inference that for low cost servo in your software, you need to have a compensation near 0 degree, decrease the value by 14%. Near 90 degree, decrease the value by 0.8%, and near 180 degree, increase the value by 2% to get somewhat corrected rotation by the servo. Now, if you make a lookup table with some intermediate values also, 45 degree, 75 degree, 60 degree, etc., then your precision will increase obviously. What are the compensations that we need to give when running at this and this amount degree? by the server. Now, up to this, I have come to the end of today's servo control. Just I will show you a few slides, and that slide I thought that, to be interesting, and these more slides are based on question raised from yesterday's class. Yesterday's lab I have faced questions, and from that I have prepared some slides so that I can give the demo. Actually, the answers were not readily available, so I had to prepare slide to give these demonstrations. The first question asked was that adding libraries to Arduino, how to do that? In the environment, if you go for tools, there the drop box will be there, the menu, there is the manage libraries. If you click on this manage libraries, what will happen? This window will open up. And in this window, what the library you want, you can type it here. And if you type it and press the enter button, it will show you that library, whether it is available or not. Obviously, net connection is required. If it is installed, for my case, the servo library is installed. You don't have to do anything. Otherwise, you will have to search the version. If you don't know the version, automatically the latest version will be installed. And there is an install button. You can see it is great. If you have not installed it, this button will be active. And if you click this button, automatically the library will be installed in your Arduino environment. How to use it? This is the code. For example, you have installed the servo library, then you will have to include the servo.h. Automatically the library will be included. Now the library has got some internal codes. Attach pin 9 means it attaches the servo on pin 9. But to myself, it is always problematic because I don't understand this language very transparently. I want to do these things with the help of registers so that I can understand each and everything what is happening inside. But this is the standard procedure of adding libraries to Arduino. The next question that was asked was the 10 kilohertz PWM how to produce for power electronics. Power electronic control part is out of my scope, but generation of 10 kilohertz PWM can be easily done by TCC R1B. Here we have selected no prescaling, that is 1:1 clock, because 100 microsecond is fast, it's not slow. So if you divide the clock, it will be even slow. So I have done no prescaling. Then the time, even then the time period is 4096 microsecond, much more than 100 microsecond. So for 10 kilohertz, ICR1 will have to be adjusted. I cannot allow whole 65535 to flow and create so much delay. What we will do? Let ICR1 equal to X, which gives ICR1 equal to 1600. As soon as you put ICR1 equal to 1600, the time period will be set at 10 kilohertz. Now, what will be the pulse width? It can span a value, OCR1 can span a value between 0 and 1600, because I have given the highest value as 1600. In this way, we can control the 10 kilohertz PWM for doing some other purpose. So my part is over. I thank you again for listening to this lab session.
Thank you, sir,
Thank you, sir,
for your wonderful
for your
session.
wonderful session.
Thank you, Vishenduda.
Thank you,
I am
Vishendu.
not finding. Is there any question?
Is there any question?
Any more questions for
Any
today?
more questions for today?
It is possible to generate high
Possible to
frequency,
generate
say 10 kilohertz PWM pulse for power electronics converter, ISO, Arduino Uno.
Arduino Uno.
That has been answered
That has
already.
been answered already.
That answer is explained.
Okay.
Okay.
So I think there are no
So
further
I think there are
questions
no
today.
further questions today.
So thank you very much. I hope that you have. I have tried my best for this lab session. Hope you have enjoyed.
Okay. So I shall send you a consolidated certificate of appreciation
certificate of appreciation
for both the days
for both the days
in your mail. Okay.
in your mail. Okay.
Okay, thank you.
Yesterday I had shown you a
Yesterday
glimpse.
I had
So
shown
for
you a
both the
glimpse
days.
for both the days.
Yes, I have seen that.
Thank you very much
Thank you very
for
much
giving your time.
for giving your time.
Okay. So good day
Okay, so good day.
and
Thank you,
good day
Ramana.
to all
Good
the
day
participants.
to all the
Tomorrow we'll meet
participants.
again
Tomorrow we'll meet again
sharp at 9:50
at
a.m. in the
9:50
morning.
in the morning.
So we are closing the session.
Closing the session.
Goodbye, Vishenduda.
Goodbye, Vishenduda.
Goodbye. Have a good day.
Thank you, sir. Goodbye.